Switching gears a little bit, okay, let's turn our attention from cost functions to revenue functions. Okay. And here's the idea, right? We can model revenue functions very simply, right? So we can have R of X, right? X being the sales of X units of whatever your commodity is, right? It's P times X, right? Well, this is your price per unit, and this is your number of units, right? Real simple, right? Um, it doesn't honestly get much crazier than that. However, often uh, you don't get to control the price, right? The price is influenced by a ton of other factors. You might have competitors. You might have any sort of other thing that's affecting this, right? It turns out the price is, as a whole, determined by a market equilibrium. But one of the things that we do know, right, is that the unit selling price is based on the quantity demanded, right? This is how wholesale works, right? So my price depends on X. So now it gets a little bit more complicated, right? Because now P is a function of X, okay? Um, P is our demand equation. P is some function of X, okay? Thus, right, our revenue function becomes X times our demand function, right? Where f of x tells us the price uh, with a given, amount demanded, and then you multiply that by the number you're demanded, and that gives you the amount of revenue. If we wanted to look at, marginal revenue, right, we could do a similar thing to what we did right at the beginning, right? Calculate, R of X plus 1 minus R of X, right? And that would give us the actual increase in revenue for selling one additional. However, we can make a similar argument to what we made right at the beginning, right? And develop a marginal revenue function, say R prime of X, right? Um, which is going to approximate, right? Just as the marginal cost function approximated the additional cost, creating one more unit, the marginal revenue function is going to approximate, right, the additional revenue created by selling one more, right? It's going to measure the rate of change of our revenue function. And then finally, right, using this revenue function, we can define a profit function, right? Um, and we can define this profit function exactly how you would expect, right? R of x wasn't a very good R. R of x minus C of x, right? You just simply subtract the two, and that's going to give us our profit function. And then, of course, we have a marginal profit function, P prime of x, you know, which approximates the actual profit, you know, um, or loss, right? That you would realize from selling one more, assuming you sold X, right? Um, so that's a lot of information, right? But let's take a look at an example. So let's say, I don't know, say you're selling speakers, right? In my undergrad, I was an audio engineer. So say you're selling, speakers to some touring company, right? They tour and they work with bands and all that. Um, and your price function, right, is minus 0.02x plus 400 if x is between 0 and 20,000. Okay. We can model our revenue function, right? That's x times p. So it's going to be minus 0.02x squared plus 400x, right? Then our marginal revenue function, taking the derivative, right, is going to be minus 0.04x, right? Because remember this point, this 2 is going to drop down, multiply. We're going to subtract 1 plus 400. And then this function, right, if we were to choose some value, right, I don't know, calculating r prime of 2,000, right, that's going to be negative 0.04 times 2,000 plus 400. It's going to come up to 320, right? So what that tells us is that if you have sold 2,000 of these speakers, and then you go to sell the 2,001st, you're going to get an approximate revenue, right, realized of $320, right? These marginal functions assume that you've gone up to this point and then say, okay, well, what happens if we do one more, right? Then say, right, that our cost function for these speakers is 100x plus 20,000. Okay, here's what we can do, right? We can calculate our profit function, right? It's going to be r of x minus c of x. Okay. Well, so what's our r of x? Well, our r of x, we know, minus 0.2x squared plus 400x. And then we're subtracting 100x's and subtracting 20,000, right? So that's going to give us a total of 0.02x squared, looks like, plus 300x's minus 20,000, okay? So here's what we can do with this, right? I'm going to copy this and move it to another page, right? This is p of x. And there's a couple of useful pieces of information here, okay? One, we can graph this function, right? I'm just going to sketch a graph really quick. We're going to have an x-intercept of minus 20,000, right? And it's going to maybe look something like that. Y equals p of x. And you could absolutely go through and do all of your 118 skills, factor this and graph it. I encourage you to practice that with this. Maybe you can find a nice way to factor it. Maybe the best way is just to plug it into the quadratic equation and find the zeros that way. Okay. And there's automatically some interesting things here. One is that our profit is going to have a maximum here, right? So that's interesting, right? We should probably try and aim our business so that we're selling this many, right? But here's another thing that we can take a look at, right? Let's take a look at well, what we did before, right? Let's look at the marginal profit function. And the marginal profit function can be minus 0.04 x, right? plus 300, right? So, that's a fairly simple derivative to take. But what happens if I plug in 2000 to this, right? We plugged in 2000 to our we plugged in 2000 to our revenue, and when you run the math through, you get about 220. And so what that tells us again is that assuming you've sold 2,000 of them, then if you were to sell the 2,001st, make about $220 a profit. It's pretty good, depending on obviously how often these sales are happening. I have one more idea to sort of end our conversation in this lecture with. And that's the concept of elasticity of demand. Okay. And so here's the idea of elasticity of demand. Okay. So say we have F is a differentiable demand function. Okay. As we know, not all functions are differentiable, but most of the ones that we work with are. Okay. Defined by x equals f of p. Okay. Then the elasticity of demand. So we're measuring something. Hopefully, we're measuring it with a highlighter, not the eraser. We're measuring something about our demand equation at the price P is given by E of P. It's the negative of P times F prime of P divided by F of P. Okay. Here's the idea of what we're looking at. Okay. We're looking at how changing the price changes demand at a certain price. Okay. So assuming we fix a particular price, how does our demand change sort of around it? Okay. Where this sort of comes from is if you look at, say, the percent rate of change of our demand function divided by the percent rate of change of our price, right? That's going to get you the negative of this guy, okay? And then economists prefer to negate the quantity. Why that negating matters, we'll have to wait until we dive into chapter 4 and sort of look at what it means for a derivative to be negative. But we can sort of take a look at this and sort of get its use in practice and look at what its analysis will tell us. Okay. Let's go back and look at our speaker sales, right? So if we recall, we had that P was minus 0.2x plus 400, right? And so, well, what we can do, right, this is our price per a given demand. What we can do is we can solve this, right, kind of flip it around, and solve for x in terms of P, right? Subtract 400 over here, divide by negative 0.02, right? And we're going to get solving for x, we're going to get that x is now a function of p, which is what we want, is negative 50p plus 20,000, right? So this is going to tell us, at a given price, what is our demand, okay? Now, wanting to calculate the elasticity of demand here, we're going to have that f prime of p, right? Well, that's just negative 50, okay? Therefore, E of p is going to be negative p f prime of p over f of p, okay? Simplifying this a little bit, right, we're going to be negative p, or rather negative 50p over minus 50p plus 20,000, right? And if you do some factoring here, you're going to get p over 400 minus p, okay? And let's look at two particular instances. We'll copy down our equation just so we don't forget it. It's p over 400 minus p. And let's take a look at E of, say, 100, then down here, E of 300, okay? So E of 100 is going to be 100 over 300, right, which is going to be 1/3. And here, E of 300 is going to be 300 over 400 minus 300, or 100. So that's going to be 3, okay? And our question is, what does this mean? Like, can this tell us anything about our situation? And it turns out that it can actually tell us a lot, right? So recall that our P is the price we're setting it to, okay? And that our elasticity of demand gives us our behavior when we like wiggle this guy a bit, okay? So here's what we know, right? Picture these guys as telling you a ratio, because remember, we're looking at the rate of change of f over the rate of change of p. So what that means is if you fix the price at $100 a speaker, okay, then if you increase the unit price by 1%, your demand will decrease by 1/3, right? Because remember, there's a negative out in front of this guy, so we have to flip all of these interpretations. Likewise, if you fix your price at if rather you start pricing it at $300 per unit, right? Increasing the unit price by 1% will decrease demand by approximately 3%, right? That's what this tells you, right? At a price P, an increase in the price of 1% will change the demand by E of P percent, right? Where we have to remember to flip the sign because E of P starts negative, okay? So here's a bit of important information, right? Sort of given that, right? So if E of P, there's sort of three situations. We have greater than 1, E of P is equal to 1, and E of P is, who would have guessed it, less than 1. Demand is so if E of P is greater than 1, we say that demand is elastic. If it's equal to 1, we say it's unitary. And if it's less than 1, It's inelastic. Okay. And a thing that I want you to notice, right, is in the previous example, right, our demand was elastic when P equaled 300, right, when we were pricing it at $300 a unit, but it was inelastic for P equals 100, right? This sort of tells us, right, that when demand is elastic, a small percentage in change will produce a greater percentage change in the quantity demanded. And when demand is inelastic, the opposite is true, right? A small percentage in change in the unit price will cause a small percentage of change in the quantity demanded, right? However, a thing to notice, right, is if we're unitary, if we change the price by a fixed percent, then our demand is going to change by that exact same percent, right? Because E of P equals 1. Using these same ideas, actually, we can take this and apply it to the notion of revenue. Rather than, say, writing, right, this is our revenue equation, right? Rather than writing P is a function of F, what if we wrote X as a function of P, right? That would remodel revenue as a function of P, which is fine, right? So we would have P times F of P, right? Now, if we take the derivative, right, notice what happens. When we take the derivative, we're going to need to use the product rule here, right? First one, the derivative of P is 1 multiplied by F of P. Then we're going to add P is fixed as prime of P, okay? But now notice, if we factor an F of P out of here, right, we're going to get 1 plus P F prime of P over F of P, which is precisely the negative of my elasticity of demand, right? Now, if we suppose that demand is elastic at our given setup, right, then this is greater than 1, so this is greater than 0, right? And since my F of P is always positive, right, that means that my R prime is decreasing, right? So what this means is that a small increase in the unit price when P equals A, right, for some elastic value, right, that a small increase to the unit price results in a decrease in revenue, whereas a small decrease to the unit price gives us an increase in revenue, right? Similarly, we can go through an argument with elastic situations, right? And show the exact opposite, okay? And this is going to sort of sum up in what actually ends up as a really nice model, okay? And so this is what we get, right? Let's say we have some revenue function. I don't know, they look like that, right? Y equals R of P, okay? And there's this point right here, right in the middle. Do it like this. And from here, we have E of P is less than 1. And here we have that our elasticity is greater than 1, right? It's elastic, okay? And right here in the middle, we have that E of P equals 1, right? And this is what that analysis told us, remember. If demand is elastic, this is greater than 1, so this is negative, so this whole thing is negative, right? So the rate of change is negative when my demand is elastic, which makes sense, right? All of these tangent lines are going to have negative slope, right? So demand here is elastic. Similarly, demand here is inelastic. Right? And so what that means is that here, right, if you increase the unit price, you're going to get an increase in revenue, right? By a small amount, right? Simply looking at the tangent line. This tells us that if you increase your price by a small amount, you're going to increase your revenue by a small amount as well, right? Because the slope of all of these tangent lines are positive, and based on what we saw here, that's forced to be true when E of P is less than 1. Whereas here, an increase results in a decrease in revenue, and a small increase in price results in a decrease in revenue, and a small decrease in price produces an increase in revenue. When demand is elastic, there's this inverse relationship. When demand is inelastic, there's not, right? They move in the same direction, right? And then here, right in the middle, right, then an increase in the unit price, well, it's going to stay about the same, right? Because our tangent line right here is flat. So if you step a little bit this way, you're going to, stay on this line, and everything is going to remain about the same. That's going to wrap it up for this part of the lecture. Come back to the next part to learn about higher order derivatives and what happens when we continually take derivatives.